to page 14, and today we're going to go over inverse trig derivative notes. Last day of new material. Okay, next week we're going to start reviewing. Okay. All right, let me just read through the notes here. So we have 6 trig functions, but none of them is one-to-one. So what that means is, let's take for sine function, for instance. One-to-one means that our graph is not going to pass the horizontal line test. So if it doesn't pass the horizontal line test, it's still a function. It just means that its inverse won't be a function. So that means, sine, cosine, tangent. If I draw a horizontal line, I'm always going to be able to hit more than one point, which means that the inverse is not really a function. However, we can call them inverse functions, inverse trig functions, because we are restricting the domain so that it's restricted to one-to-one, convenient one-to-one interval covering all the ratio values. So normally the inverse sine graph would just continue. Imagine the sine graph just kind of flips sideways. It will continue, and you can imagine that it's just not going to be able to pass a vertical line test unless we forced it to just stop and end or begin and end at specific points, right? If we don't let it continue past certain points, then the dotted lines will indicate how the graph will look if it continued. But if we stopped it, then you can imagine how the graph will pass a vertical line test, and it will not. We can quote unquote call it a function because we've restricted the domain. Okay, so arc sine and sine of x are inverse functions. This means that arc sine of x equals x, and sine of arc sine of x is equal to x. If you think about the previous inverse functions that we talked about, e and natural log, right? E and natural log of x are inverse functions. If I put an inverse into the function, or vice versa, I'm able to just get x to appear. Same thing, if I do sine of arc sine of x, or if I do sine of inverse sine of x, if I put inverse into, or function into its inverse, they're always going to cancel each other out. Now, arc sine and inverse sine, these are interchangeable. So sometimes you may see a notation showing inverse sine of x. Now, this -1 is a special notation. It doesn't mean what you normally think -1 means. It doesn't mean that we're raising sine of x to the negative first power. Okay, that's not what it means. It's just a special notation for inverse function. But sometimes you may see it as arc sine of x. So you just have to get used to the fact that we have 2 separate ways of representing inverse functions on the AP exam. Sometimes they present it this way, sometimes they present it this way. There's no rhyme or reason. It's just, just 2 different ways of representing. Okay. Now we have 6 more derivative rules to memorize. However, I want to talk about how really it's not as complicated as what you would think it is. Now, look at the pattern that I have these inverse trig derivatives written out. Very similar to the way that I had trig derivatives written out, right? Sine, tangent, secant, cosine, cotangent, cosecant. But instead of that, we just put arc in front of it. Okay. Similar pattern in the sense that all the arc trig functions that have c's in them or starts with c, they all are still going to produce negative derivatives. So that's a nice carryover from the original 6 derivative rules. Now, something even nicer is that really there's only 3 rules to worry about, because if you look at arc cosine and arc sine, what do you notice? they're the same, just a negative version, right? Arc tangent, arc cotangent are the same. Arc cotangent is just a negative version. Arc secant and arc secant, arc secant and arc cosecant are the same, just arc cosecant has a negative. So really, we're just going to be focused on trying to memorize these three rules, because if we can memorize these three rules, we can just carry them over and make negative versions of them on the right side. Okay, I'm going to talk a little bit more about ways to kind of help us recognize patterns and hopefully allow us to memorize these rules a little bit quicker and easier. But I'm going to do some inverse trig review from last year. So let's look at example 1 here. It says find tangent of arc cosine of root 2 over 2. Now, whenever you see this notation, this is a nested trig representation, right? So what we want to do is we want to just go ahead and focus on the inside portion. Okay, so whenever you see arc cosine of root 2 over 2 or arc tangent of a value, understand that this is really saying, what would the situation look like if cosine of theta is equal to root 2 over 2? So sometimes I like to write it this way. It feels more straightforward. But let's create a situation where cosine of theta is equal to root 2 over 2. So I know that this lives on the unit circle, but I want to kind of give a way that we can always do this, just relying on triangles and Pythagorean theorem. So what will the triangle look like if cosine of theta equals root 2 over 2? We're going to create a triangle. Okay, cosine, SOHCAHTOA, where does the root 2 and 2 go? Adjacent over, yeah. Okay, adjacent over hypotenuse. Now we're going to, this information alone can allow us to find that missing third side, right? A squared plus B squared equals C squared. Two plus B squared equals 4. So now that we have the triangle populated, we're now going to turn our attention to the outer trig ratio. What's tangent of theta equal to? Yep, root 2 over root 2, which is just 1. So that's all we do. Okay, so we use the inside information to populate the triangle, and then our answer is just taking the ratio of the outer trig. Okay, we're going to apply that to number 2. Number 2, we definitely need it because it's not a unit circle value. So any questions so far with 1? Okay, so looking at number 2, we want to find cosine of arc sine of 5 over 13. We're going to look at that inside portion and just think about what will the triangle look like if sine of theta is equal to 5 over 13. Okay, sine of theta, where does 5 and 13 go? Okay, A squared plus B squared equals C squared. Okay, so then we turn around and ask ourselves, what is cosine of my triangle here? Cosine of theta. Yeah, and that's our answer. Okay, just review from last year, right? Any questions? All right, turn to the back. Next page, page 15. Okay, example 3 same process. It's just that now we're dealing with variables, but we're still going to apply it the same way. Okay, secant of arctangent of 3x. We're going to focus our attention, try to gather information from just that inside portion alone. In other words, this is saying, what will the triangle look like if tangent of theta is equal to 3x? Now, we like to see numerator and denominator. I don't see a denominator, but I can force a what in a denominator here? 1. Right? 3x is the same thing as 3x over 1. But just seeing that 1 there is just beneficial for populating our triangle. Okay, so our triangle here, first quadrant. Where does the 3x go? Where does the 1 go? One is below Jason. Okay, Pythagorean theorem, a squared plus b squared equals c squared. Okay, hypotenuse. And now we turn around and ask ourselves, what is secant of theta going to be? Secant is related to what? Cosine. Cosine is adjacent over hypotenuse, so therefore secant is so hypotenuse over adjacent, right? Okay. Yeah, just root 1 plus 9x squared over 1, or just the square root. Okay, we're going to use this later on when we're trying to clean up our derivative. Okay, so any questions here with example 3? There's a way for us to find the derivative using implicit method. I think that's good in terms of reviewing implicit rule, but we're really not going to use this method to find the derivative. It's good if we forget about the derivative rules, but it just takes too long, and we want to be efficient, especially with a problem that involves like product, chain, quotient. We don't want to have to go through this implicit method. So I'm going to skip going through the implicit method, but I do want to talk about patterns to hopefully help us process these derivative rules and work towards memorizing them a little faster. So you guys can turn back to the first page, and I just want to revisit and talk about these derivative rules in further detail here. So if you look at arcsine, arctangent, arcsecant, these are the only 3 significant rules we have to memorize. Again, arccosine, arccotangent, arccosecant are just negative versions of the ones across. But I want us to discover patterns to help us remember or memorize these rules a little bit more efficiently. Okay, so I'm going to write these over here again and talk about how I kind of process and derive these rules using patterns that I see. Now, look at these 3 rules. It looks like a mess, right? These 3 rules, there's so much going on here. But look at these 3 rules and tell me what patterns, what similarities do you see between these 3 rules, right? The more similarities we can gather, the more easier it is to kind of figure them out when we need to write them. Good. Right, so they all involve fractions. All the numerators are the same. So that's not the issue, right? The issue is the denominator that looks like a mess. The numerator is not an issue to remember. So they all have u prime in the numerator. Okay, the messy part comes from the denominator. Okay, now I want you to look at all the denominators and tell me what similarities do you see between all the denominators? Yeah, they all have 1 in u squared. So that's something that we can use to help us remember at least parts of it, right? So this is how I kind of go through and build my rules here. I start with the easiest one. Arctangent is the easiest one, simplest looking one. There's no square root, there's no absolute value, there's no minus sign. It's just 1 plus u squared. So I start there. So committing that to memory hopefully is easier than these other ones. Okay, so I really am not committing the other ones to memory. I just use this one to help me build my way to my other rules. Okay, so from here, I look at the arcsecant. I know the arcsecant is the messiest one. It's got the absolute value. It's got the square root. It's got a minus sign. So that helps me remember, okay, I know there's an absolute value of u that's sitting out in front. I know there's a square root involved. Arcsecant, arcsine looks the messiest because they both have square roots. And I think the hard part is remembering, wait, what does the order look like inside the square root, right? How do I know what's an easy way to remember how the order goes? So the way that helps me remember it is, I know there's absolute value of u here, and I know that the u's are next to each other. So the u's are next to each other, and I know that I have u squared and 1. That helps me remember that it's going to be u squared minus 1. I know the u's are next to each other. And if I can build this pattern, I know that my arcsine is going to be the opposite pattern. There's still the square root here, but instead of u squared minus 1, my arcsine is going to be 1 minus u squared. So that's how I kind of build my rule. I start with the easiest. I know my arcsecant is messy, but it has the u's next to each other, so it helps me remember what to put inside the square root. And if I can put that in the order that's correct, I can just change the order to fill out my arcsine. Okay, so hopefully we'll get a chance to practice building these rules over the course of the next week in preparation for next Friday's test. All right, so but for now, the rules are available for us to use. Let's go to the back page and let's talk about example 4, relying on the rule. I put the rules above so we can have easy access to them. Okay, number 4 says find the derivative of arcsine of x. We have the rule here. Arcsine of u is u prime over square root of 1 minus u squared. What's the u value that applies for this problem? Just x. Okay, so here's my derivative. Y prime equals. Okay, what's u prime going to be if u is x? Just 1. Divided by the square root of. Yeah, 1 minus x squared, right? Just the original u value. Okay, just follow the rule and do what the rule says. Yes.
So we're ignoring those steps that are there. Right?
Yeah. We're not going to do the implicit method. We're just going to rely on the trig derivatives. Yeah. Okay, example 5, arctangent of 4x. What's our u value? Okay, so try that. See if you can work your way to the derivative using the rule above. Yeah.
On the test, if we do like u squared first and then 1,
that's fine. Yeah, that's fine. But for the other rules, the order does matter because of the minus sign.
Yeah.
Okay. All right, u prime over 1 plus u squared. Make sure that you don't just put the square for the x. The square is going to impact both the 4 and the x, so put that in a set of parentheses. U prime over 1 plus u squared, and then you can do a little bit of cleanup, make that 16x squared. Okay, number 6, what's our u value? All right, so let's practice using the arcsecant rule. Now the 2 is just a coefficient, so that's just going to hang out in front. Okay, it's just going to attach itself to the derivative. Okay, so look at the rule above for arcsecant and see if we can apply that rule. Okay, the 2 stays. U prime, 3x squared becomes 6x. Absolute value of u. Square root of u squared minus 1. Here's my u value. All right, we can do a little bit of cleanup. It's okay that we can cancel out values inside the square, inside the absolute value. So 6 and 3 can take out, reduce to be 2. I can take out one of the x's. And now let's just put all this under one fraction. So 2 times 2 is 4. And then 9x to the 4th minus 1. Okay, questions with 6? Okay, take a look at 7. Anything stand out about number 7? Product rule, yeah. That x is separate from the arc cosine 2x. We got to go through product rule. Try that. Oh, for number 6, I guess we could have, but the 2 is a coefficient, so we just treat the 2 as just attached to arcsecant. So I would say that you only have to do product rule if there's a variable expression times a variable expression. If you did product rule for 6, it wouldn't be wrong. It's just you just feel like you'll do more than you need to. You don't need to go through product rule. Our cosine's derivative is the same thing as arc sine, just with a negative in front. So negative u prime over square root of 1 minus u squared. Okay, a little bit of cleanup. Okay, questions with 7? Okay, what's different about number 8? Is number 8 going to be product rule? right? It's inside, right? It's the u value, right? So you can think of it as cosine of u becomes negative sine of u times u prime, which is basically chain rule. Or if you want to go through the trouble of saying that, well, I guess you can think of it as outside portion being cosine and the inside portion being arctangent. That's fine as well. But either way, we got to deal with that inside outside portion. A little bit of a chain rule here. Okay, so y prime equals outside's derivative, cosine becomes negative sine. Times the inside's derivative, arctangent becomes u prime over 1 plus u squared. Yeah, but you can just basically go through cosine's rule as well. Okay, basically what we're doing, just negative sine u times u prime. Now, we want to be able to represent our derivative as algebraic terms. So we can actually go through what we did with example 3 to clean this up. Okay. So example 3, we talked about how we could fill this out. We can populate a triangle using arctangent of x and find the ratio of that triangle using sine of that triangle. So we're going to step aside here and try to clean up this portion here. Arctangent of x is same thing as saying, what will the triangle look like if tangent of theta is equal to x? Now, x over what? X is the same thing as x over 1, right? Makes it easier to populate the triangle when you have a numerator and denominator. Tangent of theta, opposite over adjacent. Pythagorean theorem, a squared plus b squared equals c squared. Okay, so we can replace this whole thing here. What's sine of arctangent of x? What's sine of theta? Hmm. Yeah, we're going to hold on to that negative as well, right? So it's going to be negative opposite over hypotenuse. And then the original u prime, we need to include that as part of our derivative as well. Okay, being multiplied, there's no need for common denominator, but we can merge this together because we can think of this as the same base with just different exponent. This is 1 plus x squared to the first power. This is 1 plus x squared to the what? 1/2. What can I do if I multiply bases here?
Cancel out one.
What can I do with the exponents if I multiply bases? Add, right? So 1/2 plus 1 is 1 plus 1/2. 3 over 2. Yeah. Okay. Okay. Does everybody see how I was able to merge these together here? This is 1 plus x squared to the 1/2, 1 plus x squared to the first power. Add the exponents because the bases are the same. 1/2 plus 1 is 3/2. Okay, questions? Okay, let's do some more derivative practice. So if you can go to page 17, and we'll just work through those problems except for the very last one. So 39, 44, 46, and 47, page 17. Okay, does anybody still need this page? Okay, so page 17, try number 39. The rules are at the top of the page. Keep the 2, and then just follow the rule u prime over square root of 1 minus u squared. It's okay to leave all that mess inside the square roots. Okay, number 44, just have to rewrite that square root of x to get it ready for power roll, right? Then you can move on to that u prime. Go to power roll for that u value. That's my u prime, divided by 1 plus u squared. Do a little bit of cleanup. I'm going to bring that x down to the denominator, but it's only going to be in the denominator of my numerator space. I will resolve this complex fraction with my next step. Dividing by 1 plus x, the same thing as multiplying by its reciprocal. All right, you can flip that 1 plus x up to the top as 1 over 1 plus x. Do a little bit of just merging into one fraction, and that's all I need. Okay, question with 39 or 44. Yeah.
If we leave it unsimplified, or like with like any of these problems, like how like simplified ones?
If there's a complex fraction, just try to get it down to one fraction.
Okay.
Yeah. How about 46? What do you see there? Product rule. Yep. Product rule. F prime G plus FG prime. Okay. Any question with 46? Okay. 47 is going to feel like number 8 on the previous page, right? Just a little bit of a chain rule. Sine of u becomes cosine of u times u prime, right? It's not product rule. It's a function within a function. Okay, try 47. Yeah.
Oh, I never got that. I'm just asking if you can.
Oh, which one? Number 47?
Yeah, the chain.
Okay, sure. Yeah. Does anybody still need to look at number 46? So think of this as sine of u, okay? This whole thing is u. This is not sine of x times r, because it's sine of u. So if you think of this as a u value, then you know the derivative for sine of u is cosine of u times u prime, right? So just follow that rule then. Right, cosine of the original parentheses times r cosine's derivative, and r cosine's derivative, you can rely on the rule above. Cosine of u times u prime. Cosine, r cosine is pretty much the same thing as arc sine, just with a negative in front. Negative u prime over 1 plus u squared. Oops, sorry. Square root of 1 minus u squared. Okay, questions so far here? Now, we talked about how on previous number 8 that we had to clean this up, right? We want to get this down to algebraic expression. But here, we don't have to go through our triangle because what do you know about this? What's easy about this? Cosine of r cosine. These are direct inverses of each other, right? So what will this just give us?
1.
Close. Just t, right? Cosine, arc cosine, they cancel each other out. It's just whatever whatever that inside portion is, that's the only remaining part. Now we can just represent h prime. Put that under one fraction. Okay, questions? Okay, anybody still need this page? Okay, so you guys have a little bit of homework from 5.6. I will check this on Monday. I'll send out a link to some of the homework problems as well as the solutions and the homework page. I had a help session this morning going over chapter 5. I'll also have another help session on Monday going over chapter 5 recovery for your recovery test. And then Tuesday will be the recovery test, either at 7:15 or 3:30 to come in, recover up to 79. But you can also choose to wait until you get your trig test and let that recover or replace your lowest test grade. All next week, we're just going to be reviewing for our test. So the trig unit test will be next Friday. We'll start reviewing on Monday. We have 4 days to review.